sure.
Yeah,
so
I noticed that yesterday. You have one.
that's another. Unfortunately, a couple of them are too big now. That's the joke. You know how a couple of times you gave me the 4X, which was great at the time, but now I could wear it like a tent.
Finally.
Yeah.
Okay, so I think it says the meeting is now streaming on YouTube, so we have to become serious.
Yes.
We will try our best.
Okay, so I will disappear from the screen and go and have my coffee.
Okay.
Okay,
But I do exist.
Okay, perfect. We still have some minutes to go.
So, Lionel, how it works? You present the speakers or?
I will introduce all of you. I will give a little comment about how we can organize the talk, and then you can go.
Okay.
Yeah, what I am doing more or less to advise you how you are with time and organize the things is I will turn on my camera when 5 minutes are left, and that's it.
Okay.
An alarm.
Okay.
Promise not to not do anything weird.
No, don't worry.
So how's going on, Francesco, there?
Good. Pretty good. I think after the beginning of the phase 2, we found the pace and the rhythm with all the protocols and the things. So I think now it's going pretty well.
I will request you and Belen if you can stay after Dave talk today, if you can. I would like to check with you if we can use the breaks rooms to do the practice, or if we need another account. If you need another account, there is no problem. But if we can organize with our account, I think it's better.
For tomorrow morning?
No, for the afternoon, for the practical session.
Ah, yes, for the practical session. Okay.
This is going to work or not. So I would like to test with you both there, and I will assign an extra person just to be like a third person, and I will do the same here.
Sounds great. Yeah. And for tomorrow, the break room, how do they works? Like,
the idea we will meet I don't know 10 minutes ahead. We will have already generated the 6 breakout room, and then we will assign. We have a list of the people who to be in each of the breakout rooms, and we will have one row of an hour and then another row of another hour with a second group each.
okay. So we just need to join on the Zoom link for the workshop, and then you will split the people.
Exactly.
Okay.
Lionel, I put there the reminder of the YouTube thing I sent to, but I don't know that.
I know we did a mistake today in the morning because Florencia was using the host computer, but I think now we remove it.
Okay. So what is the host computer? I think I'm a host right now, but I'm not sure.
No, you are.
Hey, Marce, how are you doing?
Yeah, we are co-host.
Because it's the way that we found in order to avoid interruption with the microphone, so we cancel out the microscope. The microphone. I make this mistake that time. Then, anytime that somebody wants or raise a hand, we unmute and. But if we give you the co-host rights, you can unmute yourself, unmute another person, unmute people. You have all the rights. Share screen, anything. Okay. So, do you want to start sharing, Francesco?
Sure.
So, and, we are 1 minute ahead. I will start introducing our first speaker in the second section of the afternoon section of the application talks today. Dr. Francesco Palomba is postdoc at the Laboratory for Fluorescent Dynamics in the Biomedical Engineering Department at the University of California under the supervision of Professor Michel Dickman. I met Francesco when he visited the LFD as a PhD, and then he joined the LFD as a postdoc, as I say in a minute, working with Michel, and he is focusing in understanding the liquid-liquid phase separation using a set of tools, a set of proofs, which are these series of proofs synthesized by Gregorio Weber, the dimethylamino-naphthalene proofs, using the new techniques that were developed at the Laboratory for Fluorescent Dynamics. I share this fascination with Francesco about the application of this proof and the study with the liquid-liquid phase separation. So I always find interesting to discuss with him about these topics, and I think all of you will enjoy his talk today. So thank you very much, Francesco, to participate in the workshop, and I pass the word to you.
Thank you so much, Lionel, for the invitation. I really miss the talks that we had when you were a postdoc in the lab. So I hope we can do this again, because we're very interesting and could get a lot of inspiration from our coffee breaks. So today I'm going to show you the an application talk about the application of the DAN probes for the protein phase separation characterization. So protein phase separation is a new paradigm that the biophysicists use to understand the cell physiopathology. They are self-assembled structures, and this phase separation occurs because the proteins, specifically proteins that have intrinsically disordered region, they self-interact and they form new membraneless organelles, condensates, that they can have. These condensate, these membraneless organelles have they can achieve several function and complex tasks. And those are very important for the understanding of the biophysics of the cell, for instance, the nucleolus or other cytoplasmic phase separation like the stress granules. So the paradigm used to understand this phase separation is to find the relationship between the type of phase and the function. And this can be achieved drawing the phase separation diagrams, which is used to explore the type of phase. You can have liquid phase, glassy or solid phase or gel phase. And this phase separation can be physiological when they are reversible. Usually they are liquid-like phase separation, or they can be pathological, like the amyloid fibers, that they are more solid-like type. The phase diagram is very important, and the characterization of the protein phase separation start with the pure protein in vitro, where you combine with different buffers or different stimuli in order to have the phase diagram. So this is a very crucial point to understand the phase separation behavior, the protein phase separation. Here in the picture, I show you some very important and very famous phase separation, both pathological or physiological, in vitro and in vivo. So the protein phase separation, they can be triggered by like an osmotic stimulus, and they can evolve very quickly. So we need methods that can track very quickly the evolution and the maturation of this phase separation. For instance, here I report the TDP43, which is a prion-like protein. The TDP43 is responsible of neurodegenerative disease. And in this model of phase separation, as you can see, the cell under osmotic stress form this puncta that they grow and maturate, and they coalesce over time. So this phase separation can coalesce, can move, and sometimes they can experience also an active transport, as you can see in this animated GIF. So for the characterization of this phase separation, we need methods that are really able to get information very quickly and on a wide scale of spatiotemporal scale. So for this reason, the state-of-the-art methods are really limited because, for instance, and also I found quite often misleading how the people report the techniques. For instance, like the NMR, the temporal scale that NMR can access is very, very short, like picosecond, but to get this information, you need to acquire for a couple of days. And most of the techniques are very slow to get the information, and they are not compatible with living organism. So the techniques that give us the highest spatiotemporal resolution is for sure the fluorescence microscopy. But for the characterization of the phase separation, we have, for instance, here we have listed the state-of-the-art methods, and some of them are very slow to achieve the information and the spatiotemporal resolution needed. And another important thing is the phase separation. If you need labeled proteins, and it's been found that having different fluorophore bound to the intrinsically disordered protein, the protein that unmix and drive the phase separation, you can have different behavior. So labeling the protein with GFP or M-cherry, you can have different phase diagrams. And so this is something that you want to avoid if you want generalize the phase diagram. So another a well-known technique is FRAP, for instance, that is you can get the access to the diffusion and the recovery of fluorescence after photobleaching. But as you can see, to get this information, you have to average, you have to measure the same droplet, the same phase separation over time, and in vivo, can be in living cell, this can be quite challenging. So for this reason, my focus is on the application of the fluorophore, some fluorophore that can give information about the functional information, like the nano environment polarity, like the DAN fluorophores, in particular ACDAN, PRODAN, and LAURDAN. Why? Because as you could see in the previous presentation, these fluorophore are sensitive to the environment thanks to their charge separated excited state that can interact with the surrounding molecules, and the emission and the lifetime of the DAM probes can shift from blue to green as a function of the type of environment. So in very apolar, not polar environment, you have a blue emission, and in polar environment you can have green emission. And this quite often depends on especially in living system, depends on the water dipolar relaxation, or more general, the solvent dipolar relaxation, which is the interaction of the solvent molecules with the excited state. Those probes are very, very useful because they are bright, photostable, and they show low cytotoxicity. So this makes particularly useful for the application in living cells. How you can characterize the spectral shift with a spectral detection and with FLIM, or quite easily with a two-channel detection, the famous generalized polarization. And it's very easy to implement these techniques in more or less almost all the optical systems. So these fluorophore can be used to be like widely applied for the protein phase separation. I'm showing today ACDAN, PRODAN, and LAURDAN. The water solubility of these molecules drops as a function of the length of the residual chain, and ACDAN is the more water soluble, and LAURDAN is the less water soluble. So we test the DAN probes on a model phase separation, and we use the simplest protein that we found in the lab, which is BSA, because BSA phase separation can be controlled by the crosslinker, the glutaraldehyde, and by the protein concentration. The phase separation is pretty easy. You get the BSA, you put the BSA in acidic medium, and the BSA unfold, and then thanks to the crosslinker, you can get BSA quasi-orvate of phase separation. And the phase separation can be the morphology and the number of droplets that you can get. It depends on the protein concentration and the glutaraldehyde concentration. We started with state-of-the-art techniques to understand what kind of recovery using the BSA FITSI labeled, but this phase separation is a chemical bond, because the cross-linking is a chemical bond between proteins, so you can't see any recovery. The recovery is almost zero. And the FCS in solution shows that even in the presence of droplets, you still have proteins that can effuse in solution. But saying that, we move to the application of using the DAN probes. And our first hypothesis is these three probes are partitioned in different environment, both in the droplet, in solution, and this partitioning and localization depends on their chemical affinity and in principle the water solubility. So using these three probes, we can experience different environment, different region. We can probe different region within the phase separation, within the droplet, and in solution. So we started. So one important thing is we can analyze and characterize the spectral shift thanks to the spectral phasor, and we can get information of the droplet and the surrounding solution by just simply applying a threshold mask on the image and getting the center of mass of the phasor of the spectral phasor. So the spectral phasor, just a quick overview, is a way to represent the spectrum. The spectrum increase the wavelength in anti-clockwise direction, and the width of the spectrum increase on this radial direction. What is important is we can monitor the spectral shift as a variation of the angle. So we can monitor the water dipolar relaxation or the solvent dipolar relaxation, the polarity, the nano environment polarity, just simply measuring the angle of the center of mass of the phasor. So for us, an increase of the angle means an increase of polarity of the system. So we start with the characterization of the BSA phase separation, and with these three different probes, and we saw many different types of nano environments. So this means these phase separation probably can be heterogeneous. They have different pockets that they show showing different polarities. So at the beginning, we try to combine all this information in a water dipolar relaxation multi-parameter phase diagram, trying to summarize all the information. When firstly we show this phase diagram to Michelle and Enrico, they said, Ed, but guys, you should come out with an index, with something that we can measure. So we address doing that, we move to and we focus on the characterization of ACDAN. and to build up an index or a certain kind of way to represent and the emission spectrum shift of these probes in the phase separation, we have to change paradigm and model. So as you could see, these probes are well used for the characterization of the membrane model for the membrane. And this is more or less, this is in a very rough way, the model where you have the Lordan that is inside the lipids and the proton that is going toward the solution. But for the phase separation, we don't have a 2D structure, but we have kind of a 3D lattice model where we have different networks of proteins. So probably we need to eventually change the model on we represent these probes in the phase separation, changing model of the system. So using this model, we focused the characterization on the ACDAN. And we start to say, okay, let's verify if the crosslinker is able to really change the nanostructure of this phase separation. And to get that, we label the BSA with fluorescein isothiocyanate and rhodamine B, and we carried out a FRET assay. FRET is an energy transfer process, and energy transfer efficiency depends on the distance, on the nanoscale distance between donor and acceptor. The FRET assay works exciting the donor and collecting the emission of the acceptor, and the efficiency can be done measuring the decrease of the lifetime of the fluorescence lifetime of the donor. So we compare here two different amount of glutaraldehyde of crosslinker, and we demonstrate that changing the crosslinker independently by changing the ratio of donor and acceptor, the energy transfer efficiency always increase. So this means increasing the crosslinker concentration, you get probably a more like a tighter protein network. So we are really changing the nanostructure of these of the BSA phase separation proteins. So thanks to that, we move to the understanding of the potential of the host guest site within a phase separation, and to do that, we explore the emission spectrum of ACDAN as a function of the concentration of the ACDAN. And we found that this phase separation have the BSA phase separation have autofluorescence. This is due glutaraldehyde. This is well known. And thanks to the Phasor approach, the Phasor 3 components are mixing, we are able to recover the spectrum even in the presence of the autofluorescence contribution. So we choose this concentration of probe that is the first point of saturation of all the possible host gas site for ACDAN inside the protein droplet. So doing that, we've been able to recover the emission spectrum in the water dipolar relaxation with a three component Phasor analysis. And with ACDAN, we explore many more conditions for the phase diagram. So this is, it's a little bit, there are a lot of information that I will describe later. So as you can see, we've been able to get this beautiful phase diagram for the droplet phase, but at the same time, we have information also in the surrounding solution. And this is very important because the phase separation is always an equilibrium between the droplet phase and the surrounding solution. So those are the images of the phase separation. Especially as you can see in the inset, this is how the things become more crowded of droplet, increasing the protein concentration and the crosslinker. So The description of this system is a little bit complicated. So just, okay, so let's start with the solution and let's move along this axis. So let's keep the BSA concentration constant and increasing the crosslinker. What we can see, the emission spectrum doesn't change. So this means the crosslinker, the glutaraldehyd, is not affecting the ACDAN emission, and this is nice. This is important because glutaraldehyd is very reactive. Then let's try to explore this axis where we keep the glutaraldehyd constant and we increase the protein concentration. As you can see, the emission spectrum of ACDAN tends to shift towards bluer emission. This can be due to a crowding or excluded volume effects, or can be due to the interaction of ACDAN with BSA, like an interaction in the BSA pocket. So then let's move diagonally and explore the phase, the solution surrounding the droplets. In the first step, we can see a blue shift of the emission, and I think this can be due to the increasing of oligomers, because increasing the protein concentration and the crosslinker, we can see the formation of aggregates, and probably they can offer like a binding pocket for, like a hydrophobic pocket for ACDAN. And then increasing the glutaraldehyd and the protein concentration, we reach this region where the free BSA in solution surrounding the droplet, it's very low. So we can see an increase of the emission wavelength because there are less protein available in solution. Then let's move to the droplet phase. We can see two different regions. One very low polarity, which is this one, another and at lower crosslinker concentration. And increasing the crosslinker concentration, we can see very high polarity. So here we have in principle two different kind of environment. One where the water is completely bound to the inner channels of the phase separation of the binding pocket. So ACDAN is experiencing a very low polarity environment, while a very high concentration of glutaraldehyd, and we can see ACDAN is experiencing like a polarity, like a free water. So the question here is these two environment due to the water, or is more to a combination of the water and the polar groups available inside the phase separation? So in order to understand that, we are trying to characterizing and correlating the ACDAN emission with other properties. For instance, the recovery after photobleaching of fluorescein, and compared to EGFP, to see if the droplet can be populated, or the environment can exchange molecules in and out the phase separation, depending on the size and the chemical affinity. And we can characterize the concentration available in solution of molecules with FCS. In this way, we think we want to correlate these properties with the ACDAN color emission, and in order to get what kind of host guest properties these phase separation have. So to conclude, we demonstrate that ACDAN emission shift depends on the protein lattice that change at nanoscale level. We've been able to explore a phase diagram of BSA changing the protein concentration and the crosslinker concentration. Thanks to the Phasor approach, we've been able to recover the ACDAN spectral shift also in presence of a background autofluorescence. And I want to conclude saying these probes are very powerful fluorophores that can be used for the understanding of the biophysics of the protein phase separation. And here on this movie, is the last experiment that I have been done, which is the lysozyme crystal. As you can see, we have the crystal. This is very big. It's kind of more than 100 microns. And we have this tiny little defect that is an amorphous particle, because the crystallization of the lysozyme start with amorphous particles that then self-organize themselves and form this beautiful crystal. As you can see, ACDAN showed completely different fingerprints. So those are very encouraging observation to keep continuing the characterization and the project. So I want to acknowledge Michelle, Enrico, Lorenzo, and all the LFD family. And then I would like to thank Lionel for the invitation, and Dave. Last year in November, Alex and I, we went to Hawaii, and we had a very beautiful time. Thanks.
Thank you very much, Francesco. Fantastic. I really enjoy the presentation, and the results are incredible, beautiful. Well, we will have time for probably one question. I'm trying to figure it out in the audience, if there are anyone. People can also raise their hand, and we can unmute. Okay, Pablo Munoz, give me a second and we will unmute you. You can make your own question.
Hi, thank you, Francesco, for the talk. Hi, Frank. Thank you for the talk. I was just wondering. So you did this in vitro. These measures were not in the cell.
No. Yeah.
Yeah. I was wondering because you're seeing this shift in the aggregation when you increase the level of BSA. And thinking in application in my area with the neurons, I'm going to start to work in Parkinson soon. So I was wondering if it is possible to use this kind of approach to study oligomerization of proteins or disruption of membrane of organelles, in a way to understand if there is in time accumulation of protein. I will see shift if I combine this fluorophore in a special setup.
So for the application in vitro, you have to be sure that the ACDAN localized or the DAN probes localized with the phase separation.
Okay.
When I said the oligomerization, I meant in solution, so the surrounding of the phase separation. You know, in the cell, there are so many other possibilities. So it can be in the surrounding of a phase separation. You have membranes, you have other things. So I don't know if you can access that information. For the oligomerization study, Michelle and Enrico are very famous for the number and brightness. So it may be possible that it's more straightforward to use other technique for the oligomerization. But yes, if you change the crowding in the surrounding of the phase separation, you can probably have a response of the ACDAN or especially the ACDAN. So if the crowding of the crowding of the environment in the surrounding of the phase separation change before and after the formation and the devolution of the phase separation, you can maybe see a changes in the emission spectrum. Yeah.
Because you have this image of the prion that you were measuring, are you thinking to go back and study that again? Because it's very similar to one of my questions. Say this oligomerization.
Yes.
Will happen in some neuron that are dying or something.
Yes.
Thinking.
Yes, I'd like to move to the characterization of this system with the probes. There are still some technical things that I'd like to understand better before moving to to the in vivo, to the cell. And for instance, this is a clover expressing protein, and the clover expressing protein is not compatible. The green fluorescence is not that compatible with ACDAN emission. So we need to reconstruct the protein and the plasmid and all these kind of things. But yes, in future I will move to the cell for sure.
Okay. Thank you.
Okay, thank you very much, Francesco. There are another question from Luis Fatoli, but if you don't mind, I will move to the breakout room so we can try to continue with the agenda. Thank you very much.